Hello again. This is Mark. Okay, we've played with this is the AOScope program, and we've got it running on a Nano. And this is you guys we've already been through all of this. Okay, so what we wanted to play with a little bit is the clock signals, and we're going to use another little toy to be able to see them a little bit better. I mean, the AOScope is significantly limited. This is an analog discovery 2 by Digilant. I really strongly suggest you get something like this. They're a little bit pricey, but I mean, you'll use it a lot and for many classes. And if you decide you ever want to build something at home, this is really what you need. Okay, but so we'll use this to investigate how good the clocks are on the AOScope program. So if I put these two things next to each other, let me just plug it in. Okay, I've got the ground wires already connected across here, so I can connect it in straight. So this whole blue bus bar is already ground. So I'm going to connect one there, and I'm going to connect this into this 1 minus channel 1 on the bottom side. Now this unit, I made this little adapter here. It's really easy to make one of these. So okay, so I've got that connected. Now I want the signal. Which one do we want to start with? Clock C is always running when this thing boots up, so let's just go for that. And that comes out on D12, which is clear over here. It's a little bit hard to see. I'm reluctant to get the camera closer, but we may have to do that. And put it on this. Okay, so this is, now I've got the signal going onto here. Now I need the program. So the machine's going to be really boring, so let's go back up in recent items. This is program's called Waveforms App, and this is how this thing starts up. I say I want an oscilloscope. Let me get me out of the picture here a little bit. Okay, let's see. I've got a run button here. Let's tell it to run and see if it's going to do anything for us. I haven't made any adjustments to it. You can see it blipping up occasionally. Now this is a 5-volt processor, and we're expecting it to give a 5-volt pulse out on the data line, so that would be pretty normal. I've got channel 1 and channel 2 over here. We don't need channel 2 right now. I'm not connected to it, so I'll click that to turn it off. Offset 0, range 500 millivolts per division. That's a little bit small. We're coming out at 5 volts, so it'd be 10 divisions high. I want it way less than that. So let me flip this to 2 volts per division. Okay, so 5 volts will get us up 2.5 divisions. So there it was on the left, but we're not triggered or anything like that. So we need to set up the triggers. Now clear up here on the top. We've got it's in auto mode. We do a little bit better with normal. Now it's not triggering at all. We're watching channel 1. We're looking for a rising edge and the level at 0 volts. Well, it doesn't really go below 0 volts, so that'll never trigger. So let me just set that up to 1 volt, and I can just pick it or I can type it, either way. So, okay, so there's our pulse. We want to know how, the default, let me bring that up. Okay, so here's the AOScope program that we've played with before. And the clock C, I know it's small text, I'm sorry. Clock C, the divider ratio makes it 100 microseconds per tick. The period between ticks is 10,000, which would be 1 second. The high time during that is 90 ticks or 9 milliseconds. So I'm expecting something in the 9 millisecond range. And we're setting at, this says 1 millisecond per division. I've got 1, 2, 3, 4, 5 divisions here. That's only 5 milliseconds across, so that makes sense. But if I take this, I can take this trigger point and I can just slide it over. We can do that on our little oscope program too. And that's still not getting me anything I want. Let me slow this down here. Let me make it, well, let me go a little farther. This is 9. So that wouldn't count. I need to go farther. There it is. This is 10 divisions across, 1 milliseconds per. So this thing is really running at 9 milliseconds. It looks like it, at least. We do have cursors, I think. Let's see, how do we make that work? There's a cursor. So it's from the trigger. So if I just put this over to here, it says that it's 8.994 milliseconds. That's within whatever we can see. So that looks all good. I wonder if I can clear that back off now. Remove. Okay. Yeah, let me remove the cursor. Okay. So, but if I come up here to my program, I should be able to change this now. And let me make the pulse much shorter. Let's say we're saying that the clock is high for 90 of those ticks. Let me change that a little bit. Let me say I want the clock C to be high for, we won't change it too much, for 50. And you can see that the output changed immediately. So now this thing is only 5 divisions wide, or it should be just exactly 5 divisions wide. So let me slide this over to there so we can see it. 1, 2, 3, 4, 5. Okay, that's good. So that seems to work. Let's go down to the other side. Let's make it really, really narrow. And I mean, this is clock C, so it's software driven. Its smallest is going to be one click or 100 microseconds. So if I say clock C high for 1, then we get this really, really small pulse here. And let me expand that out. Okay, my base up here is 1 millisecond per division. Let's go to 100 microseconds per division. It slipped off to the left because it's still, I was off to the edge before I moved the time base. So I can come up over here and I can say this 4 milliseconds. I really want that to be 0. So I can just put 0 in there and it'll just put me there. Okay, 100 microseconds per division. Here's my 1 division. That's doing what I want. Okay, so that seems to work okay. If you're watching it really close, you can actually see that it's updating about once a second. And it's pretty close to that. So, I mean, that clock C seems to be doing what we want. Now, the impressive clock is clock A. That's got a 16-bit hardware timer on it, so we have a lot more options with that. Let's see. Clock A, right now it says CAX. So clock A is off. And if I grab my program and bring it up here, clock A output is on D10. Okay, right now I'm on D12. So let me move that down 2 notches. Okay, so now I'm on D10. So this should be our other clock. Let me put this out of the way. Oh, the other number I need is I want 1 microsecond per division. So let me put the divider, 1 microsecond per click, I should say, on the counts for this thing. It could go a little faster, but we'll play with some of that too. So I want a divider set to 2. So I want to do the CAD2. Okay, let me slide this out of the way. Come up here and do CAD2. Okay. You can see we've got a waveform on here already. And in this thing, it's really small text. Ooh, let me me and display. There we go. Okay, so I typed in the CAD2, and it immediately changed that CAX to CA1 microseconds underscore P. It's these random numbers from something else. Okay, but I want the period to be a little longer than that. Let's make it 20 milliseconds in length. So I want 20,000 of those clicks at 1 microsecond to make it 20 milliseconds. I've got a reason for this. Okay, so I want CAP, which is the period. I want it to be 20,000 of those clicks. Okay, and we could see that that kind of square wave went away. Now 20 milliseconds, I can check that. I'm at 100 microseconds per division, so I need to go up. Let me go up to, if I say 5 milliseconds per division. Okay, so here is 1, 2, 3, 4. 4 divisions, 5 milliseconds per. That's my signal. Now, if I'm playing with them, let me flip back to DocuCam. if I'm playing with something like this, a hobby servo motor, I don't know if you realize what that takes to drive them, but I mean, you know, it's got 3 wires. One of them is power, one's ground, and it's 5 volts. So, I mean, I can plug this in, but the pulse that drives it, it needs to be repeating pulse every 20 milliseconds, and the pulse has to be between 1 and 2 milliseconds. So, okay, so I've got my 20 milliseconds there. So what do I need to do to get that pulse to the right width? Let me zoom in on this one pulse again. So I've got my pulses that are 20 milliseconds apart. Let me zoom in on this one pulse. And I'm going to change this down to 1 millisecond per. Okay, so this pulse needs to be between 1 and 2 milliseconds. So this is 1 millisecond per division. So I need it to be stretched out to either here or here. And we'll go right in the middle. And we'll go for 1.5 milliseconds. So if I want a millisecond when I've got 1 microsecond clicks, that'll be 1,000. So if I say CAH for how long I want it high to be 1,000, you can see that we've jumped exactly to the 1 millisecond point. So let me go right in the middle between the two. So let me say CAH 1500. So it'd be 1.5, and you can see the line right above the trace there. Okay, so we're exactly at 1.5 milliseconds. Now let me go back to this guy. Okay, I've got a black wire. Let me connect the black wire in. That'll go to ground. Let me take the red wire, the plus wire, and let me connect that to plus. I heard the motor go. Okay. And now let me take the signal, which is the white one, and I want it on that same pin. I want it on D10. And it moved again. Okay. So let's see. Can we get everything in here at once? I don't think so. Okay, so let's see. Me, dock, and display. Okay. I know it's busy. A lot of stuff on the screen at once. Okay. Let me move this down to here. Okay. And I need this to come up a little so you can see what I type, and I want this guy to come up a little so you can see the waveform. At least the top of it there. Okay. So this is, the pulse that's coming out is 1.5 milliseconds in length, and it repeats every 20 milliseconds. So now if I say CAH, the low end is going to be about 1,000. So let me do the 1,000. And watch the motor turn. Okay. CAH 1100. A little bit. 1200. A little bit more. We'll go back to the middle. And so I can test my servo motor out with this program. I can make it go any which way I want. The highest it should go to is about 2,000. That's about the end of it. I'll go back just a little. So you could, so for testing out a servo motor, you don't even need to write any programs. You just can type in what you want for the pulses. So it gives you really good control. The other thing that I want to do with this clock is let me disable unplug the servo motor. And let me go back and get rid of that. Okay, so and I'm going to bring this up so we can see it better. Now, I can specify a frequency in this program too. I can just say clock A, CA, F, and I can say 1K. Oh, K has to be uppercase. CAF1K. Okay, that's saying 1 kilohertz. 1 millisecond per division on this thing. And you can see that, we get a full waveform in 1 millisecond. Let's go up higher. CAF10K. And, those are too tight to see. So I can come in here, change my time base from 100 to 100 microseconds per division. So now, in one division, I'm 100 microseconds, I'm 10K. Well, let me go up faster. CAF 100K. So we're at 100 kilohertz. If I put a speaker on it, I couldn't hear that. Human hearing doesn't go quite that high. Okay, so let me bump this up by 10. I can go to 10 microseconds. Now we're starting to see a little bit of artifacts because, this is starting to get a higher frequency. We're at 10K or 100K, 100,000 times a second. That signal's jumping up and down. Makes it really easy for me to see. We can go farther. I could say I want to go to a megahertz. So I can say CAF1 capital M. There's 1 megahertz. Let me, again, change my divide ratios up here so we can actually see it. Now we're starting to see some really interesting artifacts because now we're at megahertz speed. 1,000,000 times a second this thing's going up and down. So the oscilloscope has got its limits too. I mean, this analog discovery. This is way beyond what the microprocessor's AOScope program could possibly see. We're 10 times the sample rate on that. But with this thing, we can see it really pretty clearly, and it's actually running fine. You'll notice that there's something called overshoot or ringing on these signals. You can see as it comes up, and it goes down, and it rings back and forth, and it staples down, then it goes down, and it does the same thing. Okay, how fast can we go? We're still, this is divided off of a 16 megahertz clock, and it gets divided by 2, so it's only 8. So it should be 8, I think, is the max. So I should be able to say CAF8M. That doesn't work. Let's try for 4. CAF4M. Okay, 4 megahertz. That's the top. And how fine you can adjust it at that point gets really limited too. Let me jump this up here to show you what the waveform. It starts looking pretty ugly. This is really pushing the limits of what we're looking for. Plus, we need a good scope with regular probes, and that you'd be able to see this just fine. With this, no, not so much. But we can see it. It works fine. Most of the stuff we do, in this classes just don't get up to those frequencies. Okay, let me just CAF. Let's do. I can go back to 1,000 hertz, just to show you that that's exactly where it sits. The ringing is still there when we're sampling this fast, but you never see the other side because it's so far over there. So the base is going to be. There's back to the 1 millisecond per division. Okay, so we can see all this stuff with clock A. Clock B is just like clock A, except it doesn't have as much resolution. So when you set it to a specific frequency, it'll just be kind of close. Maybe not that close, but you just kind of have to play with it and see what you actually get. Okay, that's all I want to cover in this one.